My name is Cesare Carazza, and I'm the mission commander of Spacesim. And today we are hosting a former member and Lisgar student, Doug Sinclair. Doug Sinclair is an aerospace engineer and founder of Sinclair Interplanetary, a satellite hardware manufacturer producing primarily star trackers and reaction wheels. Currently, more than 90 satellites incorporating Sinclair Interplanetary hardware have been launched to orbit. And remember, this is an open Q&A session, so make use of the raise hand feature if you want to ask a question, or if you prefer, you can type it in chat and I could ask it for you. I do have a set of questions myself that I'd like to ask every alumni that we interview, which can help develop our conversation. So, Doug, to begin, could you please introduce yourself to the audience in your own words?
Sure. Hi, everybody. Really happy to be here today. My name is Doug Sinclair. So as you've heard, I was a Lisgar student back in the day, I guess from 1989 to 1993. And I was involved in space simulation in grades 9 and 10. And And then, so the reason I'm speaking to you today is I founded a satellite hardware company called Sinclair Interplanetary, built a lot of equipment, and then in April of 2020, I sold Sinclair Interplanetary to a company called Rocket Lab, which primarily builds launch vehicles and then also builds some satellites and does some other space things. So I'm now down in New Zealand working as an engineering fellow for Rocket Lab.
Okay, that's a great introduction. So one question that has been sent into me was someone wondering what your post-secondary education was.
Sure, yeah. So left Lisgar in 93, went to the University of Toronto to do engineering science. And the way that program works is the first 2 years of engineering science are a broad, sort of all of engineering. And then at the end of second year, you choose a discipline to focus on. And I chose the aerospace engineering option. So I graduated there with a bachelor's of engineering science aerospace option. I then went to the University of Surrey in Guildford in England to do a master's degree. So I did a master's by research in satellite engineering. So that was a 12-month master's, the sort of thing that you can only do in the UK. And that was the entirety of my post-secondary. So I got a bachelor's and a master's.
Great. So Evan in the chat is asking, does this company specialize in any specific part of the satellite, or do they do it all?
So no, we absolutely specialize. So here I'm talking about Sinclair Interplanetary. So Sinclair Interplanetary is all about attitude, determination, and control. That's a lot of long words. What does that mean? It's about pointing your satellite in the right direction. And you think about that, there may be a number of reasons why you want to point your satellite. Your satellite may have some solar panels. The solar panels probably want to point towards the sun in order to get some power. And you sort of point them roughly at the sun. You may have some radio antennas, and the radio antennas probably want to point at the Earth where you're talking to people. And so you want to point your dish sort of at the Earth, and maybe you have a requirement of a couple degrees to point that. Or maybe you've got a telescope on your satellite. Maybe you're looking up at the stars. Maybe you're looking down at the ground and you're taking high-resolution photos of the ground. That telescope needs to be pointed phenomenally accurately generally to thousandths of a degree. All the way to maybe you have a laser communications device. Maybe you've got a laser that you're pointing at somebody else and you're sending information over that link. That laser could need to be pointed to hundreds of thousandths of a degree. So various satellites have various different pointing requirements and run all the way from a few degrees pointing to very tiny fractions of a degree. And so to do this, you need two types of equipment. You need sensors that tell you, where am I pointing now? And then once you know where am I pointing now, you need actuators to turn you to point to where you want to be. So I made both of those. I made attitude sensors and attitude actuators. And so the sorts of sensors that I'd make, so I made a sun sensor. The sun is a nice bright object. If you can measure the angle between your satellite and the sun, you know something about where you're pointing. So that's something that can solve your problem to a couple degrees, and it's cheap and simple. And then I made stir trackers. So for a stir tracker, just imagine you've got a webcam and you've sort of bolted a webcam to the outside of your satellite. And this camera is just looking up at the sky and it's seeing these points of light. It's seeing the stars. And then what you do is you've got a computer in there that is capable of looking at this little pattern of spots, recognizing the stars by their characteristic patterns, and determining very accurately which way you're pointed. So that's half of what I do, figuring out where you're pointed. And then the other side is pointing you in the right direction. And there's a couple ways we can do that. So I make reaction wheels. So you can think of it sort of like a gyroscope, but you've got a flywheel, a big piece of metal that can spin around, connected to an electric motor. And if I accelerate that wheel, if I spin it faster and faster, I'm putting a torque on that wheel. That puts an opposite torque on the body of my satellite. So if I have 3 wheels whose axes sort of are lined up with your X, Y, Z axes, then I can put an arbitrary torque on my satellite and point it wherever I want. And then the final thing, I know this is a very long answer to the question, the final sort of actuator we make is something called a magnetic torque rod. So if I have a bar of iron and I wrap it in copper wire and I put an electric current through it, that bar of iron turns into a magnet. And it's got a north pole and a south pole. And that's going to want to swing and line itself up with the Earth's magnetic field, just like the needle on a compass wants to line up with the Earth's magnetic field. So again, if I have 3 of these bars of steel and I can put electric currents through them in either direction, I can generate a torque against the Earth's magnetic field, like that needle of a compass. So yeah, that's what I do, is pointing satellites. And so that's Sinclair Interplanetary, the company that I built over about 20 years. They're still doing that. The office in Toronto is still making all that equipment. And then I moved over to Rocket Lab down in New Zealand, and I'm now working as an engineering fellow there. So that's sort of a senior position where I get to poke at all sorts of different engineering problems that people are having. So I still do a lot of satellite work, but I'm now also starting to do some launch vehicle work. So looking at rockets, which is new for me. That's exciting.
Okay, so we have another question in chat. What are the many challenges you faced when you were setting up your company?
So I guess I can sort of split that into maybe 2 categories. There's the what were the challenges of running a space company, but then also just, what are the challenges of running a company? So I guess on the space side, the biggest challenge in setup is the space heritage problem. So space is very conservative. And I don't mean that sort of politically, but like nobody wants to take a risk on a new thing because space missions are fantastically expensive. So, if I'm building a $5 million satellite, I don't want to, and you come to me and say, oh, I've got this new computer. You should use my computer. Well, like, what if it breaks? Then my whole mission's gone. So whenever you're trying to sell something in the space business, the customer's first question is, okay, so when has this flown in space before? But of course, you're never going to get something in space unless somebody takes that first risk to fly it. So yeah, that's a real that's a barrier to get into the business. And then once you're on the first side of that barrier, it actually sort of helps you because it keeps competition out. Conservatism is great all of a sudden once you are the de facto standard. But so that's a real challenge in space. In terms of just business, the biggest challenge is just managing cash. Generally you need to spend money first and then you get paid second. And so it's always just how do you have enough money to start? I'll tell you just a brief anecdote. When I first started the business, so you do the work and then you'd send an invoice to your customer, and generally an invoice is payable within 30 days. So you'd send out the bill and it would say, payment due on this date. And I sent out the invoice, and then like a week had passed. Oh, well, they haven't paid me yet, but I guess, okay, maybe they need 2 weeks. And I was waiting, and then 30 days hit, and they hadn't paid me yet. And my mind I just couldn't understand what was going on. I sent them a bill. It's a 30-day bill. They haven't paid me. What's going on? And when I realized that in industry, nobody pays on time, and there's nothing you can do about it. Generally, your customers will pay you a few months late. I've had customers pay me a year late. And that's just sort of how it works. But that blew my mind, and I just did not know that was a thing until it happened.
Okay, great. So I was sent in another question, and someone was wondering, what was the first component you designed and you started like producing and you sold to someone?
Sure. So, all right. So you remember I was talking about magnetic torque rods, which was a bar of iron. You wrap it in copper wire. You put an electric current through it, and it sort of becomes a magnet. So I had a clever idea for how to do that better. Because the thing about a standard torque rod like that is, if you want it to be a magnet, you have to keep putting electric current through it. As soon as you stop putting electric current through it, it stops being a magnet. And so there's this continual power drain when you want to use it. And I thought, well, wouldn't it be interesting, instead of using a bar of steel, to use a bar of magnet material? And then instead of putting a small current, a couple amps through these copper windings, to hit it with a pulse of hundreds of amps for a short period of time. And I could magnetize that bar of material. And then I don't need any more electrical power. It just stays a magnet. But then if I want it to be magnetized in the other direction, I hit it with a pulse, a short pulse of high current, and I can reverse the magnetic field that's stored in that thing. So I thought this was very clever, and so I built a prototype of this. I didn't have a customer or anything. I just sort of invented this thing. I built it, and I had it in this little briefcase. And I went to some trade shows, so some satellite industry trade shows, and basically, if anybody made the mistake of standing still next to me for a minute, I'd pop open the briefcase and, hey, do you want to see the demo? And I had a little compass, and I could make the needle spin around, and I pressed the little firing buttons. And so I ended up flying a few of these. Turns out it's sort of a solution to a problem that nobody has, because the small amount of power that you put into a regular magnetic torque, nobody really worries about. And the trade-off is my pulse generator. There was a fairly big electronics box, and it had some complexity to it. And so it probably wasn't a good engineering trade. But long story short, that was my first thing in space. So that's how I sort of broke that first getting a thing in space. And then I was able to do this sort of Jedi mind trick, and I don't know how it worked, but my next product was a sun sensor. So we're talking about a thing to measure the direction that the sunlight is coming in from. And like that has nothing in common with a magnetic torque rod. And people would ask, when has this flown? And I'd say, well, this thing hasn't flown in space yet. But I've done a thing that has flown in space. And so trust me, and I made this other thing too, so you should trust it. And that's a really spurious argument, but it worked.
Okay, that's great. Okay. Something a lot of us were wondering was, what is the production path of something like, what does it take to make something that goes in space? And how does that compare making something similar that would just be put in something on Earth? Like, how much more steps is there to putting something in space?
So that answer really varies a lot. So I guess it depends just how invested are you in having this thing work. So, on the one side, I'm sure you folks are all familiar with CubeSats, little satellites that a lot of universities and even some high schools have been building. If you want to build, a piece of electronics to go in a CubeSat, a lot of that can be almost off-the-shelf terrestrial things. So, there are people flying Raspberry Pi computers or Arduinos or whatever. You just pop them in your CubeSat and away you go. So on one side, like, don't let people scare you that space is this super scary place where you need billion-dollar facilities to do anything. You don't. You can get a long way with really very terrestrial things that you're familiar with. But then on the flip side, let's say I want something that will last for 15 years, and it's going around the Earth once every hour and a half, and its temperature is going to cycle, between -20 and +50 degrees Celsius every cycle. So, if I take a Raspberry Pi and I start temperature cycling it like that, I don't know how long it's going to last, but it's not going to be 15 years. Or let's say I'm not going to low Earth orbit anymore. Let's say I'm going up to geostationary orbit, where a lot of the old communication satellites are. The radiation in that environment is going to eat your Raspberry Pi in weeks. So I guess for simple things, you don't really have to do a lot. For things where it absolutely has to work, or you're going into more demanding environments, then there's a lot of stuff that goes on, and those are generally you do a lot of work on thermal cycles. Just, can the thing survive going hot, cold, hot, cold, hot, cold, hot, cold without wearing out? Rockets are a really rough ride. There's a huge amount of vibration, and sometimes there's shock when you launch something into space. So we do a lot of work shaking the units that we build and making sure they're going to survive the rocket. And then radiation. There are different amounts and different types of radiation in space depending on where you're going. But that radiation can damage electronics. It can make glass. If you have glass in your optics, it'll make the glass turn brown and eventually opaque. Radiation effects are also something that we worry about quite a lot in a way that you just don't for things on the ground.
So is it up to you to certify your equipment? Is there any sort of standardized certification?
Right, yes. So you hear this thing about space qualified, and it makes you think that there's probably some government agency that gives you a stamp and says, yes, you are now space qualified. No, there is no such thing. There is no central body that gives you the little gold star and says you're ready to go. It's all a conversation between the user and the supplier. So, if I'm selling let's say a star tracker to a customer, the customer is going to say, I want to see your test reports from vibration, shock, thermal cycles, and so on. And maybe they want to see your prior heritage, and they will look at all of this and just try to build up their own assessment of how risky is this thing. And then maybe they'll look at the competition and they'll say, well, I could buy this thing and it's got some level of risk and it's got some level of price. Or I could go to this other place and it's got some other level of risk, but maybe it's cheaper or maybe it's more expensive. And you just balance that. That's if you're in a supplier-customer relationship. Sometimes you're building your own thing. So, if you're building your own satellite, you get to choose what goes in it. I guess, but with the exception, so the launch provider, so whoever's building your rocket, they don't care if your satellite works particularly. It's not their business. They do care if your satellite falls apart and damages the rest of the rocket, or releases chemicals that are going to deposit on other things. So those are generally, if you're building a CubeSat, you have to show your launch provider that you can survive a vibration test and that you're not going to outgas material.
Great. So we have another question, chat. How did you deal with getting your company off the ground? And how did you get the funding to make your original products?
Yeah, so I had a bit of an interesting path through this. So, so I got my master's degree, and I came out of that with a net worth of $0. I struggled to actually scrape together the money to ship my stuff back to Canada. But on the flip side, it's actually very important that I need to acknowledge this, I did not come out with negative net worth. So thanks to my family, I did not come out with student debt. And I'm just going to acknowledge that privilege. So I came out with a balance sheet basically debt on zero. No assets, no liabilities. So came out of that, and I got a job. I worked for a company that was then called Dynacon Enterprises out in Mississauga, and I was building the MOST space telescope. So this was a little Canadian space telescope launched in 2003. And I worked for Dynacon for 3 years. So at the end of those 3 years, I had retained earnings from 3 years of being an engineer. So that was just, whatever of my salary that I hadn't spent. That was a chunk of money that I had. And that was when I decided that I didn't really like working for other people. So maybe I better work for myself. So I left that job and I started my company. And initially, my product was consulting. So I was just, working as an engineer, but instead of at a full-time job, I'd I'd bill you by the hour, and I'd write a report for you, and I'd do some breadboarding for you, and so on. And so the fun thing about being a consultant is your hourly rate can be sort of 2 or 3 times what it was when you were an employee. The downside of being a consultant is you're not guaranteed 9 to 5 work. You could find a week where just nobody wants your work, and so nobody pays you. So that's, that's a little exciting. But so what I did is then, in the hours when nobody wanted to pay for my work, I spent that time tinkering on my own, developing product. So I was able to do that without any external investment. I was able to just take the retained savings from 3 years of employment, and then the bit of money that was coming in from consulting to develop those first products. And then I got to the point where I had some products to sell. So I was sort of selling my time and selling products, and then got to the point where I was selling enough products that I didn't have to sell time at all. And it was only after I got to that point, which was, 5 or 6 years in, that I then got an office that wasn't in the basement of my house, like actually an office in a different building, and hired my first employees. And then that's when it really took off. So, you'll see a lot about business investing, and often the idea is, as soon as you have a business idea, you should go and get some people to lend you some money or invest in the business. I probably, if somebody had done that, I might have been able to get to the point of having an office and hiring employees on day one. So I probably took sort of 5 years to what's called bootstrap, to organically grow the company to that point. The flip side is that, so last year, after 20 years, I sold Sinclair Interplanetary to Rocket Lab. And at that point, I was the sole owner. So that means that what they paid for the company goes straight in my pocket. Whereas if in the early days I had, sold fractions of the company for investment, then, when it cashed out, I would have had to then pay that back out to all those investors. So, it absolutely worked out in the end, but it was a long road.
So earlier you spoke of heritage, and how much does this increase the price of components, and how realistic are the prices we see?
Oh, I'd say it does a few things. Yeah, it makes things expensive, because baked into the price of everything is the fact that in order to develop it, somebody probably had to do a test mission. It also, you look at a lot of space equipment and you go, wow, this looks really old. This is really low tech. We could do much better if I just went and built this thing today. And that's because, a thing that you would buy for space today, the design was probably locked in 5 or 10 years ago. And then, you have to build one, fly one on a test mission, make sure it works, and then you turn around, okay, we're ready to sell this to the larger community. And as soon as you said, okay, this thing works now, well, you don't want to change it. Because if 5 years ago I flew this thing and it had this particular microprocessor in it and it worked, now, Intel comes out with a newer, shinier processor. I can't just change to the newer part, because what if that newer part doesn't work in some way? So I become very conservative. I just don't want to change things if they've worked. In what way are the prices realistic? Maybe whoever asked that question could elaborate a little bit on what they mean. But yes, if you see a price on a price list, yes, that is generally the price that people expect you to pay. Now, if you're doing a sort of a student, an educational thing, you may well be able to get donations. It never hurts to ask for donations. Um, we everybody in the industry loves students. Everybody was a student once. A lot of us did projects like this. We remember what it was like, and so people will want to help you out. But yes, this is an expensive game.
Okay, great. I got sent in another question of someone wondering, what is your facility like in Toronto?
Yeah, so we have an old building that used to be a garment factory. So it's the sort of thing where, if you can imagine, 100 years ago, it would have just been filled with people with sewing machines, making shirts and so on. And then, of course, that business has left Toronto and gone to other places in the world. But yeah, so it's this beautiful old brick and timber building. And Sinclair Interplanetary occupies 3 floors of that now. So it's a rented building, so there are other tenants in the building. So what we have in that, we've probably got 15 people by now, slowly been growing. So we have, just desks and computers and that sort of thing. And then we have thermal chambers. So we have, think about, like something that looks like a refrigerator, big box with a door, you put things in, but it can go cold and it can go hot. And you can program it to run hot-cold cycles. So we've got 3 big thermal chambers. We have a high vacuum facility. So I've got a vacuum chamber that can pump down to very, very low pressures. We've got a large clean facility. So if you're building optics or mechanisms, you really don't want to get dust in them. We've got a large facility with HEPA filters cleaning the air that is super clean. We have, so reaction wheels. I talked about those big spinning flywheels. If the flywheel isn't perfectly balanced, then it's going to shake as it spins. So we have a big facility for measuring the forces that are coming off of these mechanisms very, very accurately to measure those sort of imbalances. We have a big facility for electrostatic discharge, so ESD. If you get a static discharge, a zap into electronics, sometimes that can damage it. So how do we know that our space electronics are safe against ESD? Well, we build them and then we zap them. We zap them a whole lot and see if we can break them. We have a large electronics assembly area. So, lots of soldering irons and microscopes and tools like that. So yeah, that's sort of what our facility is like. The thing that I would really like to get is a vibration table. So that's a big thing where you could shake an object like it's being launched on a rocket. But this is where being in a 100-year-old building with neighbors is a downside. I'm not sure we can actually put a vibration table in there. We may shake the building down.
Okay, so Dr. Magwood asks, how big of a field of view does a star tracker use?
Sure. So the star trackers that I make have a sort of a conical field of view, and it's a 7.5 degree half cone. So 15-degree full cone angle. And there have been star trackers built with various fields of view. A long time ago, I built a star tracker that had a 0.8 degree field of view, so a very narrow field star tracker. And sort of the trade-off is, if I have the narrower the field of view, so sort of the longer the focal length of the star tracker. So, you can think about it like a zoom lens. The more zoomed in you are, if I have a small change in the attitude of my satellite, so if I rotate a little bit, the stars are going to move a lot of pixels for a narrow field of view star tracker. So I become much more sensitive to rotation. So that's a benefit of having a narrow field of view, a long focal length. The problem is, I mean, let's imagine I've actually got this really big telescope as my stir tracker, and I just turn it on and I see some stirs. Where am I? I have no clue, because there are millions, billions, trillions. There are so many stirs. It becomes a very difficult computational problem to figure out where you are. So with my stir tracker, it's got a 15-degree full field of view. It carries a catalog of about 2,000 stirs that it knows about. And we consider to be guaranteed to see 3 or 4 of those stirs within that field of view. So you can just turn it on without giving it any hints, and it knows where it is. So yeah, that's the difference between a stir tracker that needs some initial guidance as to, we think you're about here, now give me an accurate answer, and what's called the lost in space problem of you just don't know. Now, if I can, so star track, there are all sorts of different star trackers. If you think about the Pioneer spacecraft, so launched out of the solar system in, I guess, the 1970s. So they had a sun sensor. Very easy to build the sun sensor. The sun is just the brightest thing you're going to see. And then they had a special stir tracker that looked for Canopus. So, I mean, Canopus is just one stir. So this star tracker just found Canopus. And then knowing where the sun is and where Canopus is, that gives you 2 vectors. That tells you where you are. And of course, Pioneer, that satellite spun. So the Canopus tracker was continually spinning through space, and eventually, Canopus would pass through its field of view. So once per revolution, Canopus would pass through its field of view, and it would go ping. That's my angle.
Okay, so I was sent in another question. Someone is wondering, how much is built from scratch when it comes to your components? Like, how many pre-built components are you shipping in to build your products?
Yeah, so generally, we get printed circuit boards made externally. So by that I mean, we get somebody else to send us the green and copper fiberglass boards. We buy electronic components like, we buy resistors, transistors, capacitors. We build some of our own inductors, and we buy some other inductors. But we do actually have people, winding transformers if we need a transformer with a turns ratio that we can't get out of the catalog. Then for assembly, we will make the first few ourselves. So, we've got the soldering irons and the reflow ovens and things to put all those components on the circuit board and test them. But then, so we used to do everything ourselves just like that. Now that we're in higher and higher volume, we'll now go to a fabricator. Once we make sure the design works, we'll then go to a fabricator and say, please make 100 of these, and we'll get robotic assembly of those circuit boards. Piece parts like screws and washers, we'll buy those. All of our machined components, so we use an external machine shop, but basically every piece of metal, started off as a big block of metal, and a CNC milling machine cuts that down to exactly the thing that we want. So we buy basically no pre-made assemblies. We make everything. We have everything made for us.
Okay, great. So another question which was asked is, how much software development is required?
Yeah. So I've said that we build almost all of the hardware sort of custom. We're not using a lot of pre-made stuff. Same goes for software. So we don't use any operating systems on any of the electronics that we fly. So yeah, all of the software is what I would call bare metal software. So, it's just assembly and C code just running natively on the processor. So yeah, basically we write all of our software. And that varies. So some little things like a reaction wheel, I use a little 8-bit processor for that. So it's an 8051 processor, but you can think of that. It's sort of like an AVR or a PIC or any of these little sort of hobby microcontrollers you might know. The Star Tracker uses a relatively complex processor. It's an Cortex A8. So, the sort of thing that you might have found in a high-end cell phone 5 years ago. And I brought that up from bare metal. We were looking at running Linux on it, but we just couldn't get Linux to boot in under like 10 seconds, and I needed this thing to boot in milliseconds. And so the answer was just to write it all. Actually, okay, so writing all your software, it's a huge amount of work, but it can sort of pay for itself. So I had a colleague who was using an off-the-shelf Raspberry Pi, and it just running Linux. And so she had this scientific payload, and they launched it, and it was working okay for the first couple of days, and then it stopped working. And so you think, okay, like something's broken. And how do you debug a thing when it's up in space and you can't touch it? So a huge amount of debugging effort followed. The ultimate resolution was the Raspberry Pi was getting hot because it had been on for quite a period of time. It generates some heat. There's no air in space, so in vacuum gets hot. The Linux software that was running on it said, oh, I'm getting hot. I'm just going to turn down my clock speed. I'm going to run slower to prevent overheating and damage. And when it was in this slower mode, it couldn't keep up with the data interface that was attached to the other piece of the payload, and it stopped working. And so she found out that she could actually recover her payload simply by turning off this Raspberry Pi, letting it cool down. And then if you turn it back on, it would have a number of minutes of operation. You just turn it on and off, and you can make the thing work. But the point that I'm trying to get at is she didn't know that it was overheating and lowering its clock speed because Linux didn't report that. That was a piece of behavior that somebody else had written for a terrestrial application. If you write every line of code yourself, then you do know what the behavior is.
Great. So Dr. Magwood asks, are there lots of people trained in this sort of software development?
No. All right. So I'm going to say this, and I'm sure for many of you, this is just going to sound like the most ridiculous statement ever. But I am still building new products that have processors on them that have 768 bytes of memory. Not gigabytes, not megabytes, not kilobytes, 768 bytes. And that's fine. That's all it needs. They're doing very simple jobs. But it is very hard to find a software person who isn't very old who remembers how to write efficient software. We had an issue a little while ago where there was a data processor and it was receiving about 10,000 packets of data a second from some other thing. And the software person was starting a new thread for every packet that came in because it sort of seemed convenient. So this poor operating system is trying to launch 10,000 threads a second and is really burdening this computer. Whereas if you just thought, well, let's not think about multitasking and multi-threading, let's just handle each set of bytes as it comes in through the serial port, you would have been fine. You do that with far less effort. But yes, it is difficult for us to hire people who are used to efficient software writing that lets us use the sort of low power, radiation tolerant computers that we tend to be using in space, because people are generally used to modern computers where there's no benefit for saving a few bytes. Who cares? Actually, sorry, let me just expand on that. The same goes for electronics. A lot of the electrical engineers are used to, basically like building Lego. You take this great big power supply chip and this computer chip and this memory chip, and you just sort of plug them together, and there I've got my design. And if you say, well, in fact, we can't, the radiation, for example, the radiation tolerant computer that we're using, it doesn't have a clock generator. So in fact, you have to use a quartz resonator and a couple of RF transistors to try to build a clock oscillator. That's just not something people know how to do anymore. So yeah, hiring in space is very difficult. And the flip side is there are a huge amount of jobs in space. So sorry, I'm sort of going off on a little bit of a tangent right now. We're not answering the question, but there's this really interesting disconnect. I hear a lot of students, particularly Canadian students, saying, I want to work in space, but I can't. And generally it's things like, I want to work in space, but SpaceX won't hire Canadians. And so it's like, my life is over, it's terrible. At the same time, there are Canadian space companies trying to hire people and they're not getting applicants. So, if you just go look at the websites of Sinclair Interplanetary, Canadensis, MD Robotics, or MDA, whatever they call themselves these days, all of these Canadian space companies doing incredible things. They are trying to hire you right now. Well, probably after you finish university, but they want young Canadian engineers to come and work for them. And meanwhile, there's this pool of Canadians who just have it in their heads that nothing's happening in Canada, that it all has to happen in America. And then because of ITAR and sort of citizenship rules and whatever, they're not allowed to work in America. And so this is terrible.
Okay, that's really interesting. Another question I've been sent in is, how has your role and the role of your company changed since Sinclair Interplanetary was bought out, or you sold the company?
Yeah, so my role has massively changed. So I guess, when Sinclair Interplanetary, when I was running Sinclair Interplanetary, I guess I was the CEO or something. I didn't really have a title. But Cordell Grant was the COO, Chief Operating Officer. So he was sort of doing the day-to-day running of that facility. And so then when we sold, I said, all right, Cordell, you're in charge of the Toronto office. So he's now at Rocket Lab. He is the vice president of spacecraft components. So he runs that facility. And I thought it was very important that I not sort of stay there looking over his shoulder. If I've said that this is his now to run, it's important that I'm not second guessing him and saying, oh, yeah, that was an interesting decision you made, but what if you did that? That's not actually letting him run the facility. So yeah, so I left Toronto at that point and went over to New Zealand. And so at New Zealand, I'm an engineering fellow, and it's wonderful. I'm sort of in the org chart. I'm high up, but there's nobody under me. So I have nobody to directly manage, and nobody really manages me. I get to wander around and be wise. So if there are particular sort of problems that come up, I can come and work on those. I do some professional development, so I help some of our junior staff, with education and professional development, and I just sort of get to tinker on some things as well. So okay, so try to give you some concrete examples of some of those things. So you may know that Rocket Lab, quite a number of months ago now, we lost a vehicle. We had a second stage engine shutdown very quickly after ignition. And so I spent 4 or 6 weeks in the anomaly investigation right after that, trying to figure out what happened and how can we make sure it doesn't happen again. Then another thing that I'm doing is, so in Toronto, we're building this equipment in a fairly manual way in quantities 10, 20, and so on. What we're looking at doing is in New Zealand, building an automated production line where we can build this equipment in much greater volume. Because Rocket Lab New Zealand, it's huge. We've got 500 people. We've got this huge facility. We've got a big machine shop. All those sorts of things we don't have in Toronto.
Okay, thanks a lot. So another question is, what advice would you give to those seeking a career in STEM?
I mean, that's a pretty broad question, and and particularly like science, technology, engineering, math. That's a very wide field. Okay. So I mean, I could just give some random thoughts. So who here plays D&D? Is D&D cool again? Yeah, okay, we've got some hand raised. Great. So using the D&D metaphor, charisma cannot be your dump stat. So there certainly is, but for some people, so I mean, I think probably for me, when I was in high school, was the thinking, well, if I'm going to be in STEM, then I don't really need to deal with people anymore. If I'm really good at my math and engineering and things, I don't need to know how to write English. I don't need to study history. I don't need to, I don't need to be good at public speaking, all these things. I can just, sit in a little corner with my machines. That's not true. So engineering is what I can talk to most, because engineering is what I do. You spend a huge amount of time communicating with other people. So you spend time working in teams. I mean, you don't really do things solitary. You've got a team that you're working with, and then you're generally talking to people sort of above you in the org chart and the supply chain or whatever, trying to justify why you should be doing what you're doing. So I mean, an example of that is if you have customers, you're trying to tell the customer, like, you should buy my thing. Or if you're in a other organization, you might say, here's why I need the budget to do this R&D. If you can't do that, then you don't have the toys to play with. And then, perhaps as you get later in your career, you also have employees that you're managing or students that you're educating or things like that. Again, you got to be able to communicate. So yeah, I think that's, and also science. I mean, science is all about learning new things and then spreading them to the world, writing papers, going to conferences. So to boil that down, what advice would I give to you seeking a career in STEM is do a lot of STEM, but don't let that be the only thing in your life. Remember how to interact with other humans as you go down that path.
Okay, that's a great piece of advice. Dr. Magwood asks, what should we be teaching the graduate students who can do things like program in assembly language, people who know how components work at a basic level?
So like what should we be teaching them so that they can do that? Is that what the question is?
Yeah.
Okay. Well, I think hands-on experience with simple electronics goes a huge ways. You know, the little plug-in breadboard and you know, the little low-scale integration. You know, you've got a LAN gate, an XOR gate, whatever. So okay, just an anecdote from my education. So second year electrical engineering, we spent a couple weeks on diodes, like real hardcore NP doping, valence levels, the diode equations, all of that. And so, you know, at the end of those couple weeks, we were diode masters. But if you then asked somebody in that class, what does a diode look like? There would have been blank faces. At no point in that did they say, and generally a through-hole diode is a little cylindrical thing and it's got some legs coming out both ends. So we had a couple weeks of the high mathematics and sort of physics of diodes, and nobody said, this is what one looks like, this is how, you know, where you buy them, this is how you use it. So I think getting that sort of experience to couple your academic knowledge with your hands-on would be useful. And yeah, I mean, just building your own computers or just working with little microcontrollers to build things, that can be fun.
Okay, great. So another question. Have you ever designed something specifically for a given mission or ever modify an existing product?
Yeah, so from a business sense, you like to try to make the same thing for as many people as you can. No, so I guess early in my career, I did some fun one-offs. We talked about sun sensors. I built a moon sensor for one particular mission that needed to point a payload at the moon. And yeah, so in terms of modifications for particular missions, generally so mostly we build standard products. Where the modifications generally come in is the testing. So we might have a standard test that goes between minus 40 and plus 85 degrees Celsius temperature range. But we might have a particular mission that says, well, like we'd like you to test to minus 65. So, okay, so we modify the test plan, or we'd like to do a vibration test with a particular vibration spectrum. Sometimes there's software modifications. So, we have a particular software protocol that you can send commands to the devices and get information back. And generally, we ask that the customer, implement the other side of that API. But sometimes the customer will say, we're really fixed on this particular software protocol. So can you adapt your device to speak the same language that everything else on our satellite does? So we'll do some of that.
Okay, that fits in greatly for next question, which is, how does one get their satellite components that come from so many different companies to communicate with each other effectively? Say you're buying like parts for a PC, you get this one motherboard and it's going to fit this CPU and this graphics card. So how does this work when designing satellites?
Yeah, no, it's a huge problem. It absolutely is. And the funny thing is, every few years, somebody will go, I have the answer to this problem. What if everything was standard? And so somebody will publish a sort of a standards document that says, if only everything worked this way, then it would all just plug in together seamlessly. And so a few people will build some devices that are compliant to that standard. And then a few years later, somebody else will go, but what if there were this standard? And so there is this proliferation of little niche satellite standards, none of which are interoperable. So it doesn't solve the problem at all. So it's like, you've got one thing that's got a USB, and you've got another thing that's got a FireWire, and you've got, this and that. And so yes, it absolutely is a problem. So I guess there are sort of three ways you can solve this problem. You can buy all of your equipment from one place, and then it's generally interoperable. So, for example, Sinclair Interplanetary equipment plays nicely with itself. If you went to somebody like Blue Canyon, Blue Canyon sells basically every piece of a satellite, and it all sort of meshes together properly. So that's one thing you can do. The second thing that you can do is you can adapt everything to your standard. So I've seen this done. Is let's say you pick a standard, and half of the equipment on your satellite just natively supports that standard. And then for the things that don't, you put in a little box that bridges them to the standard. So, just extending that metaphor, let's say you had a FireWire widget, but you wanted your satellite to be on USB. For that one thing, you'd place a little FireWire to USB converter box. And so now you've got additional boxes on your satellite, but to your flight computer, everything looks the same. Well, the final thing that you can do, which is probably most common, is the central thing, which is probably your flight computer, just has to support a half dozen different standards. And so you end up with a flight computer that might have some Ethernet ports and some RS-422 and some USB, and it's providing 28 volt power to some things, and it's providing 5 volt power to other things. And and that thing generally has to be custom. You generally have to design that for your mission, and it's a lot of work. So this is a problem. This is a problem in the industry, and it doesn't really have a solution yet.
Okay, that's really interesting. So Evan asks, what is the moment of your career where you've been the most proud?
That's a really interesting question. So launches are nice. It's fun when you put things in space. Put a lot of things in space now. Got some things to the moon. That felt good. But I would say, actually, this isn't a single moment, but I think what I'm most proud of is having built the Toronto office and the team that I assembled. And sort of realizing this sort of mix of pride and responsibility that I built this team where I had, people paying their mortgages. I had people, raising their children, and they're all financially able to do that because we've built this company that works. So that, and really, when you come down to it, it is the people that are much more important than the little satellites in space. So I'm quite proud of just having built that thing and let those people join in that dream.
So you mentioned you have some of your stuff on the moon. So what is that exactly? And what mission?
So what it is exactly is a bit of a hole. So do you folks remember the Bereshit moon lander? So this was a project out of Israel, 3 or 4 years ago, that was going to go to the moon and land. And what actually happened is the flight computer rebooted a couple minutes before it was supposed to land, turned off the engines. And so this thing hit the moon with a fair wallop. which was not intended. So I had sold some equipment that was on that spacecraft, which we're pretty sure is entirely pulverized. But there's like this fine mist of aluminum that I made somewhere over the moon.
So you can say your stuff isn't just on the moon, but all over the moon.
Well, yeah, all over the moon, in the moon, yes.
So another question I got sent in is, what advice do you have for those going into university on how we can develop quality connections that would lead to opportunities in the future?
Yeah, so okay, so I will tell a little university anecdote. So I was woefully unprepared for university. I just, I was grade 12. I sort of, yeah, I'm going to university after this. This is, a person with my level of academic achievement. I should probably be doing a university thing. I hadn't done nearly enough research, didn't really understand what university was like. I had visited an older friend who was living in residence at the University of Toronto. And we're in residence there, and it's 2 a.m, and people are chasing each other down the hallway on rollerblades. And I remember I'm 16, I think, this is great. There's not an adult in sight, people chasing each other down the hall on roller skates. This is the life, this is wonderful. And so I went to University of Toronto, and I chose to stay in that residence my first year because this seemed great. And I just took a couple of weeks to realize, I don't want to live here. Like, there are people chasing each other down the hall in roller skates all night. Like, this is loud. You don't have any space. So no particular point to that story other than, if you're unprepared, university is not what you expect. But how do you develop connections? Do things that aren't just class. So how you're going to interact with other people outside of class, it's going to depend on what school you're at and what you're doing. In my particular situation, engineering science at University of Toronto had a common room. And this was like a lounge for the class. And, well, it's a lounge for people, but of all years. So you'd have people from first year through to fourth year hanging out there. And that was the space. That was our space. And that was where you really made these connections. But for me, for other people, it might be clubs, it might be sort of other social things, it might be sports. But yeah, there's limited connections you're going to make just sitting in a lecture hall, listening to your professor talk. And so yeah, do take advantage of every opportunity you have to make those connections. Because I am 45 years old now, and as I say, I just moved to New Zealand. And when you are 45 in a new place in the world, it is extraordinarily difficult to meet people. And so I think back to those wonderful days in university where you're all sort of thrown into this jar and shaken, and you meet hundreds of people a year. And the people that I met from university are still my closest friends all these years later. So it is a pivotal time in your life. It's probably more important for that than actually for anything you'll learn in a classroom.
Okay, great advice. And on the same subject, we were wondering, do you have any recommended aerospace programs, both in Canada and internationally?
So I'm not going to recommend a particular one because it depends what you want to do. But I will, I'll point you towards some research that you should do. So aerospace is pretty broad. If you can, figure out what bit of it you want to do. So there's space and there's airplanes. aerospace engineer, like, so when I went to University of Toronto, we did both in that same thing. So, I learned a whole lot about high bypass turbofan engines, which I've not used since at all. But I've also learned a bunch about spacecraft attitude dynamics. And, there are people right now who are building airplanes at Bombardier going, why did I have to learn about spacecraft attitude dynamics? But, so that program gave us a mix. There may be some programs that are more on space. So some of them space engineering or space applications. In my undergrad, I learned, a lot of electronics and physics and chemistry and fluid dynamics and things like that. So I thought I was prepared for, in my grad school, I had a class called satellite communications. I got this. I understand satellite communications. Well, no, I didn't, because that was all about how do you run the internet through a satellite. So it's all about the ground stations and how do you set up these data packets and things like that, which I hadn't been prepared for. So yeah, lots of different types of things within the big umbrella of aerospace. So what is it you want to do? Do you want to do airplanes? Do you want to do spacecraft engineering? Are you actually in fact interested in planetary geology, or some of the sciences that are tied to space more than the engineering? These are all valid, and they'll all take you different places. I do also just want to share, there was a guy in my program who went into aeronautical engineering and made it to third year before realizing that he couldn't do boats. He wanted aeronautical engineering because he wanted to be a nautical engineer. So please do your research.
Wait, how does this work? Did he realize what he was studying?
Well, so the name of the program was aeronautical engineering.
So you saw the nautical part.
Yeah, that's what my colleague did. My colleague really wanted to be a boat engineer. I mean, it wasn't a disaster. We learned a lot about gas turbines, the basic structures, the physics. It's all sort of the same. But I was similarly clueless in how university worked. So when we get to grad school, I realized for you guys, grad school's a little ways away. But so I show up at grad school, my first day. I say, all right, great. Here I am. I'm ready to go. And they say, that's wonderful. So who's your supervisor? I don't know. I thought you were supposed to figure that out. So you are supposed to figure out who your grad school supervisor is months and months before you show up to grad school. So yeah, don't make my mistake. Figure out what you're doing. Okay, so do your research, particularly talk to people who have been to these schools. If you're interested in a program, learn everything you can online, but then see if you can interview somebody who's in, first or second year at that program and really find out what it's like there on the ground.
Okay, that's some great advice. So I have gone through all of the questions I've been sent in advance. So does anyone have a question they'd like to ask now in chat? Okay, wait, I just got sent one on my phone. So what are your hobbies? Someone was wondering.
So I'm a pilot. It's actually, sadly, it's still in Canada, but I own a little airplane called a Mooney M20J, which is a little hot rod of an airplane. So I like to fly that, and I've been sort of accumulating ratings. So I'm now an instrument-rated pilot, which means that I can fly in bad weather conditions. So that's been fun. I like to work on old vehicles. So I've had a succession of old trucks that I maintain. Right now I have a Bombardier Iltis. So that's a 1984 Canadian Forces truck. That's basically a weaponized Volkswagen Golf. So That's been a lot of fun. Sadly, I mean, that's in Canada next to the airplane. Yeah. So I play D&D, as you may have noticed, and also this science fiction role-playing game called Traveller. So in fact, I mean, Traveller was probably one of the reasons why I'm a spacecraft engineer, because the role-playing game Traveller had a section for designing spaceships. So there were rules for designing a spaceship. You had to have a hull that was a certain size, and then you put in engines, and the bigger the engine, the higher number of Gs your spaceship could fly at. And you had, you allocated fuel tankage and calculated the crew. And when I was young, I spent hours and hours designing these imaginary spaceships for this role-playing game, and then carefully drawing out the deck plans on graph paper. And that's not so very different from what I do now.
Okay, that's really interesting. So, any more questions?
So I'm a little curious, while people are thinking, can you tell me what the space simulation is like these days? I'm sure it's changed since I was involved, but I'm curious.
Yeah, yes, it has quite a bit, especially during the pandemic. So it's all online now. So there, as you know, there's the educational aspect of the club as well as there's running the mission. So the educational aspect of the club has shifted to, well, what you're doing right now. We have been organizing these interviews. So people we've interviewed before you, we have Alexander Ghosh, who is now, he leads the astrodynamics and flight dynamics team at Northrop Grumman. Daniel Kekes, who I believe you know.
Yep.
Works at University of Toronto Institute of Aerospace Studies. Aisha Turak, professor of engineering physics at McMaster University. And Dan Serbu, who's a research scientist at NASA.
And great.
Yeah. So when it comes to the mission itself, so because it's online, we decided to send our own probe this time. So we played our own little game. So I guess we all started researching satellite parts, and we basically made a shopping list of parts, and then we had our budget, and we had to design a satellite that we were going to send. And the mission this year is going to the exoplanet Lucian B, and the mission goal is to determine whether it can support human life or not. So that's actually in the middle of running right now. So we're not doing like 1 week of mission, but instead over our Friday work sessions, we're running the mission. And that somewhat like simulates the communication delay you'd have with a satellite, which is so far out. And it gives the simulators like a week to come up with stuff.
Well, that's wonderful. Yeah, I mean, so sort of like a play-by-mail war game back in the day.
Yeah.
That sounds like a lot of fun. Yeah, so and that's actually great preparation. So in my aerospace engineering bachelor's, and I'm sure in many others, in fourth year, there's a project that is space systems design, which is it's a course, but it's a design course where at the beginning you're given a requirement specification for some sort of space mission, and you need to produce a stack of engineering documentation for what this imaginary spacecraft is going to be like. And then at the end, you have to present your preliminary design review in front of an external panel in the same way that you would if you were an engineer working on a project and we're trying to get it to the next level of funding. So I mean, you've had a great rehearsal for that.
Yeah, that sounds really interesting. Looking forward to that in university then. So is there anything we haven't touched on that you would like to talk about?
I think I've probably hammered my main points, and I mean, to some degree, I'm probably preaching to the choir, because I think most of the things I'm trying to say is engage with other people and learn how to communicate and things like that, and by being involved, by all of you having chosen to join this club and participate in this thing, you're a long way there already. So yeah, this has been a lot of fun. Thank you, and yeah, I'm excited for your mission.
Thanks so much. So, if you don't have any more questions, Doug, I'd like to thank you on behalf of all of Spacesim. This was an amazing educational opportunity for us. It was
All right.
really interesting to get your perspective, not just as an aerospace engineer, but someone who started his own company.
Well, that's wonderful. So thank you all very much, and enjoy your weekend.
Thank you, Doug.
Thank you. I guess it's already the weekend for you.
Yep. Well, it's Friday night for you. That's almost the weekend, right?
Good enough.
All right. Bye-bye.
Bye-bye.
Thank you so much. Bye.